Welcome back, everyone. The Artemis program sets the foundation for sustained human activity beyond low Earth orbit through a sequence of missions that gradually expand operational reach. The program moves from high Earth orbit to lunar proximity, and then towards surface operations supported by staged hardware. Each element is designed to function as part of a larger progression that tests propulsion, navigation, structural performance, and human systems. This structure allows mission planners to evaluate how propulsion demands interact with guidance limits and fuel margins during long-duration transfers. The central idea is to create a reliable and repeatable method for reaching lunar space that future missions can scale. These steps form a framework that links deep space transport and surface preparation into a single integrated effort. Artemis relies on a layered approach that uses proven components to support more demanding missions that will follow. Key stages include launch, translunar transfer, lunar orbit insertion, and crewed return. Each stage depends on stable mechanical relationships such as thrust generation and structural load distribution. Mission designers examine how fuel use and electrical systems influence each operational period. The approach ensures that early missions gather the engineering data needed to guide later surface work. These sequences reflect how spacecraft must function under extended strain when operating far from immediate ground support. The steps build familiarity with deep space travel by testing propulsion cycles and long-duration environmental control. Artemis hardware is built to operate under repeated structural and thermal loads created during ascent, transit, and lunar orbit operations. Propulsion events impose significant stress on tanks, valves, and thrust structures as mass flow increases chamber pressure. Thermal control must maintain stable temperatures inside avionics modules through conduction and radiation. Long-duration operations also require power systems that can manage steady output while adjusting to changing sunlight angles. These factors shape the design of crew modules and service elements that must withstand both rapid heating and gradual cooling. Load paths and thermal behavior determine how components interact when the spacecraft transitions from launch conditions to deep space conditions. Please subscribe. The Space Launch System from NASA in Washington, D.C. provides the thrust required to place the Orion spacecraft and its service module into translunar trajectory. The rocket uses staged propulsion that combines solid boosters and a liquid core stage. As the vehicle climbs, guidance systems adjust control surfaces and engine gimbals to maintain the correct pitch and yaw angles. Mechanical forces travel through the interstage structures and into the upper stage as thrust levels change. At booster separation, load distribution shifts to the core stage, which must sustain steady thrust while managing tank pressure and thermal gradients. The overall system is built to handle rapid acceleration, followed by precise trajectory shaping during upper stage burn. The Orion spacecraft functions as the crew transport system during outbound and inbound travel. Its heat shield, structural frame, and pressurized cabin must handle multiple forms of mechanical stress. During re-entry, the heat shield experiences intense thermal loading from plasma formation, which transfers heat through ablative material. The crew cabin must maintain internal pressure while external forces fluctuate. Life support components regulate oxygen, humidity, and carbon dioxide through controlled air movement and mechanical separation. Electrical power moves from solar arrays to batteries and distribution units that maintain stable voltage levels. These systems ensure the crew experiences consistent environmental conditions throughout the mission. Translunar transfer requires stable navigation paths that align propulsion output with orbital mechanics. Mid-course corrections use small reactive thrusters to adjust orientation and velocity. Each correction changes how fuel mass is distributed across tanks, which influences structural balance. Navigation algorithms measure spacecraft position relative to Earth and the Moon through optical and radio tracking. Mechanical stability depends on maintaining predictable rotational behavior while adjusting thrust direction. As the spacecraft approaches lunar orbit, braking burns reduce velocity, allowing gravity to capture the vehicle into a stable path. Fuel margins must remain sufficient for both insertion and future return maneuvers. Lunar orbit operations focus on trajectory management and thermal stability. Orbit periods expose the spacecraft to alternating sunlight and shadow cycles. Thermal control radiators must manage heat through both conduction and emission. The service module maneuvers continuously adjust orbit altitude and inclination to support future landing operations. These maneuvers rely on consistent thrust from smaller engines designed for multiple restarts. Mechanical systems must handle vibration and heat during each burn, while navigation systems track orbital position with precision. This phase establishes a stable staging point for lunar surface work and supports communication links with ground control. The European Space Agency in Paris contributes the service module that provides propulsion, electrical power, and thermal control for Orion. The module contains fuel tanks, radiators, and structural mounts that transfer mechanical forces throughout the vehicle. Solar arrays rotate to maintain optimal light exposure as the spacecraft changes orientation. Propulsion units deliver thrust for mid-course corrections, lunar orbit insertion, and orientation adjustments. The module must maintain pressure stability within tanks while managing heat from engine operation. Electrical systems distribute power to avionics, life support, and communication equipment through regulated circuits that prevent overload. Environmental control systems manage airflow, filtration, and temperature inside the crew cabin. These systems regulate how heat moves from electronic equipment into circulation ducts. Air travels through mechanical filters that remove particles before recirculation. Temperature control channels warm or cool air through fluid loops that transfer heat to radiators. Pressure regulators maintain stable cabin levels during ascent, transit, and re-entry. These functions allow the crew to operate in a controlled environment that remains steady despite changes in external conditions. The systems must adapt to variable thermal loads while keeping internal conditions within narrow limits. The Gateway concept introduces a small lunar orbiting platform that will serve as a staging location for future lander operations. The platform will test propulsion cycles, solar array rotation, and thermal management in deep space conditions. Docking ports will transfer loads through rigid connections that align spacecraft structures. Power systems will store electrical energy in batteries during sunlight exposure and release it during shadow periods. The structure must handle repeated heating and cooling as it passes through the lighting cycles of lunar orbit. These characteristics support long-term operation and prepare for increased activity around the Moon. Surface access depends on a lunar lander designed for descent, landing, and ascent. The lander will manage thrust levels through multiple engines that stabilize the vehicle during powered descent. As it nears the surface, sensors measure altitude and velocity to guide throttle adjustments. Structural legs absorb landing forces and distribute them across contact points. Fuel systems must provide reliable flow during both descent and ascent cycles. Thermal control maintains equipment temperature within safe limits throughout operations. The lander will serve as the mechanical link between lunar orbit and surface activity. The Japan Aerospace Exploration Agency in Tokyo develops several mission components related to navigation and cargo delivery. Their systems will support automated docking, precise trajectory alignment, and mechanical handling of payloads. Navigation sensors measure relative position during approach, while propulsion elements fine-tune motion. Cargo modules will manage load distribution through structural mounts that maintain balance during transit. These modules must protect equipment from vibration and thermal extremes. Each component contributes to a reliable transfer chain that links orbital assets with the lunar surface. Surface systems must support mobility, shelter, and scientific operations under harsh lunar conditions. Rovers use electric motors that convert battery energy into wheel rotation. Dust tolerance requires sealed joints and filtration layers that block fine particles. Habitat structures will regulate pressure, temperature, and airflow through mechanical systems that rely on pumps, ducts, and radiators. Energy storage units will maintain output during long shadow periods when solar input decreases. These systems form the foundation for sustained presence by creating stable working conditions on the surface. Sustained lunar operations depend on predictable power cycles and thermal control behavior. Solar arrays, radiators, and batteries function together to maintain a steady output. Structural mounts are there to secure equipment against thermal expansion and contraction caused by long cycles of light and shadow. Communication links transfer data between the lunar surface, the gateway, and mission control. Thermal sensors keep track of equipment conditions to prevent overheating. These systems support continuous research by safeguarding instruments during those extended missions. The Indian Space Research Organisation in Bengaluru, India, supports mission elements focused on navigation and resource-related experiments. Instrument packages measure environmental conditions and surface properties that influence future landing site selection. Data acquisition units collect sensor readings and store them for transmission. Structural frames secure instruments against vibration during transit. Electrical systems regulate power flow to maintain stable operation. These components expand the information base needed to plan future activities beyond the early missions. Artemis prepares for expanded human activity in lunar space by combining reliable launch systems, deep space transport, and surface capability. The mission structure links propulsion behavior, thermal control, and structural endurance into a unified sequence that supports long-duration work. Each mission will refine understanding of how spacecraft respond to mechanical stress when operating far from immediate support. The program establishes a methodical path that enables exploration with increasing autonomy. Thank you very much for watching. Please like and subscribe.